Welcome to week 4 synchronous session for integrated chemistry and physics B. I'm your instructor, Mr. Sharan. So welcome. For those of you watching this as part of your asynchronous makeup work, you will need to make sure that you have downloaded all of the proper simulators from the links in the course announcements. Also, if you are watching this and have not watched the week 3, which is part 1 of this 3-part synchronous session activity, please stop this video and go back and watch that. The week 3 video is posted to the course announcements, and where you can find the link to the video itself, the simulators that we used, the worksheets that we used, and a follow-up assessment, which is mandatory for every student. Now, if you've coming back to the video after having watched that previous video, or have already watched the previous video, or attended a live session last week, we shall begin. So, as a quick recap, in last week's session, we spent the class period going through and examining the behavior of a pendulum in a virtual environment and determining what variables could we measure, what variables could we control and purposely change, and what would be an independent and dependent variable in an experiment, attempting to answer the question, well, generally answering the question, what variables affect the behavior or motion of a pendulum? In this case, the speed at which it moves back and forth. And of those, which one specifically? So, does the length of the pendulum, which is the string length, which you can see me manipulating here, affect the time for one oscillation? So we're looking at the period, which is one back and forth. So as an example, I'm just going to show you what that means. Turning on my photo gate timer. Okay. The time it takes to follow that blue path back and forth once, that's one oscillation. That time period is referred to as the period of oscillation. If this were an orbiting object, we would say the period of rotation. So now that is our dependent variable. We are recording that variable, changes to that variable as we alter one of 3 other variables. So length, mass, so how heavy is the thing on the end of the string, and finally angle of release, which we have a variety of angles from 90 to as low as 1 degree. We can assume that 0 degrees will produce no motion. So it is not unlikely to say that. Just as we can assume that if the length of this were 0, the pendulum would not move, or if the mass were 0, there would be nothing there. So we understand that those are our setups. Now, for this, you are going to need access to this following sheet. Now, a link for this has been provided. You will need to make sure that you download a copy of this spreadsheet, as if you attempt to just straightforward enter your numbers, you'll be altering the master copy, and I don't want you to. You do also want to make a copy of this that you can manipulate, because for each of the sheets, mass, length, and angle, there is a data table where you'll fill in your data, and a graph. Now the graph is, I have already built the graph, so it will automatically put numbers in as you enter them, creating a graph shape. You'll also notice, if you take a quick look as well, I have already taken the time to go through and increment out the different variables. So I've already changed the variables in each case to give us a nice range, 0.2 to 2 here in mass, and to evenly space out the changes. This is a key component that we should always make sure that we're keeping in mind, that whenever we are designing an experiment, whatever the independent variable is that's changing, we want to make sure that the changes are always even, and we want to make sure that the changes represent a large enough range of numbers. So in this case, I have 10 numbers. 10 is usually the safe minimum that you should have for data collection. Now, That's not something that we see in all of our projects. Some of our projects require very little data collection in data points, but sometimes so the speed lab is a perfect example. Those they require far too little data points for there to be accurate measurements taking place. So we're going to make sure that we know the proper techniques. I also want you to note as well that there's one number I've highlighted in each of the data tables in red. That number is the default number. So as we alter mass, that number in red has to stay constant. So as I alter mass, then the length has to be 1, the angle needs to be 45. As I alter the length of the pendulum, while I'm altering the length, the mass needs to be 1 kilogram, the angle is 45, and as I'm altering the angles and testing them, the length has to be 1 meter, the mass 1 kilogram. So those are the defaults when you're testing the other variables. Now, let us begin. Okay? So what we're looking for here, and before we go too much further, I want to make sure that we understand one other thing that we're looking for. So the other aspect of this that we're focusing on as well is our graphical methods. Specifically, what's the shape of the graph? Now, this is where your rejection or acceptance of your hypothesis comes from. Does the actual analysis of the data match what you predicted will happen occur in it? So let's just take a look really quick at these relationships. So the first one here is a flat horizontal line. This is a no relationship activity. Whatever the y value is, or the y variable, it's a constant. Changing the x variable has no effect, so it produces a flat horizontal line. Here we have a linear relationship, or a directly proportional relationship. What we mean with directly proportional is as x increases, y increases by the same proportional value, or at the same rate. So even if it increases, by 5 times as much, every time I increase by 1 here, it's 5 times, 5 times, 5 times. So we're always even. That produces a straight line data. Also, if this were down this way, that's actually still a directly proportional. It just has a negative slope. Here, however, we have a bit of a change. So now here, when we look at this, and if we look at the curve of the shape, what we're saying is when the x value is quite low, this is almost infinitely large. It just approaches infinitely large. But as x increases in size, this decreases and approaches towards 0. Now we would refer to that as an inverse relationship, and you can see our classic y equals mx plus b, or point slope formula. The x is now 1 over x. The b for the intercept, the m for the slope, and the y are exactly the same, but now the relationship between x and y has changed. If we get this shape, this is a proportional or an exponential. So y is proportional to the square. So what we're saying here is as x increases at an even rate, y increases at a growing exponential rate. So, where this goes from 1 to 2 to 3 to 4 to 5, this is going from 1 to 2 to 4 to 16 to so on and so forth. So it is multiplying by itself as it goes, increasing rapidly, whereas this is increasing by a simple factor. We see here point slope method, y equals mx plus mx squared plus b. Finally, the final version we'll see is a squared, y is squared, and x is normal. So here what we're seeing is that when x is quite small, y is small as well, and as x increases, at first y increases really quickly, but then it starts to even out and level out and eventually reach a plateau, a maximum that it'll hit, so that as x increases, y just stops increasing as much, and it's just smaller and smaller levels of increase. So this would be something like someone who's running really fast and then slowly decreases their speed, whereas this would be someone walking and then all of a sudden starting to pick up speed and run. All right. Now, these are the structures of we're looking for, and we're looking to see does when we put a scatter plot of our data, does it make this shape? Because which shape it makes determines the relationship, which will determine whether our hypotheses are correct or not. Now, let's get back to our data itself. So, let's take a look here. All right, now, I'm going to collect some of the data for you. I'm not going to collect all of it. I do want you to collect this on your own. So this is something that you will need to do the rest of on your own before you complete the post session. But I do want to show you how to collect the data and collect a number of points. So I will collect 5 of the 10 data points that you need for each of the 3 variables, and it will be your responsibility to collect the rest for next week's data analysis. So let's start here with mass. So I'm going to be altering the mass, and I'm going to go from 0.2 to 2, incrementing up by 0.2 kilograms each time. So now remember, I'm changing the mass. I have to keep the length at 1 meter, and I need to make sure that I always release it from 45 degrees. Now, here's how we're going to collect the data, and this one's very simple. So this is going to eliminate just about all of our experimental error. There will be really no experimental error in this. Now, had we done this without a photo gate, say with a stopwatch, or with live materials, there would definitely be a number of places where we'd want to focus on where there is experimental error, but this is not the case. All right, now let's continue. So to collect my data, it's pretty simple. I just click Start. I click on the weight, and it'll automatically go here and be released. Back, forth, and there it goes. So my first number is 2.086. I enter that number, and as soon as I enter it, you'll notice the graph has changed. It is now starting to graph. You'll also notice there's a blue line here. I've set these to put a trend line on them, so even as you put your numbers, it'll also try to fit a line that goes through it. All right, so now we need to check our next data point. I'm going to reset. This time I want to, reset again. Oh, take a look. I forgot to reset this down to 0.2. I did 1, so I don't need to redo this. I just need to move this down to 2.086. So right back there. All right, so let me actually now correct this. I'm going to go back to 0.02. So I'm going down to 0.2. Start my photo gate. Click. 2.086. All right, let's check the next one. So reset. I'm going to go up to 4.4. Start my photo gate. Click. 2.086. All right, so I'm going to get 2 more data points, but we're already starting to see a bit of a pattern here already. All right, 6. Start. Click on this. 2.086 again. All right. Now, I could probably safely estimate that this new answer will also be 2.086, but we want our data to be as accurate and as empirical as possible, which means it's not a guess, it's an actual measurement. So I'm going to take one more measurement. Photo gate started, click. And I have confirmed it, 2.086. Now, Maybe the masses of below 1 is not enough to cause an effect. I would still need to test the masses above 1 kilogram, but right now we're seeing a pretty good pattern that we're getting a straight line. So let's go check the next one. So remember, you will be responsible for answering the rest of these, and you want to make sure you have a full data set before you answer the post labs, because the post labs are all about the graphs, the graph shapes, and what your data came out to be. So identifying the different types of graphs and behaviors, what your data set came out to be. All right, so I'm going to reset this to 1. We're going to keep the 45-degree angle. This time, however, I'm going to be looking at length, so I'm going to start with 0.6, and I'm going to go up by 2s. So I'm going down to 0.6. Turn on my photo gate, click on my mass. All right, so 1.6157 seconds. 1.6157 seconds. And it'll begin my graphing. All right, reset. Next thing is to go up to 0.8. 0.8, just to confirm. Photo gate on, click. And 1.8658. All right, so we're starting to get a shape, but we only have 2 points. We're not going to know enough. So this could be one of the this could either be 2 of the 5 graph shapes that I covered at the beginning of this lesson. We'll come back to those in just a second, but we need more data points to know for sure. Right now, this could be a straight line, or it could be a curve. I don't know without more data, so let's collect some more. All right, 1 to 1, so this is now our default. 2.086, which we knew because that's the same thing over here as well. All right, so we're now starting to get what looks to be a straight line. So we'll keep going from there. So I'm going to collect 2 more data points. All right, so we're doing 1.2. All right, 2.2852. Right. Now, take a look. That line that's drawn through it is not straight anymore. It's starting to curve. So we're now starting to see that the relationship isn't just a straight line relationship, but there may be actually a curve. So this now has opened up a third possibility on this. Now, if this is truly a curved shape, then that'll actually narrow it down to a single possibility, but we'll check that later. Last one. 1.4. Set this go. All right, 2.4683 seconds. 2.4683 seconds. And yeah, even more curvature appearing. All right, so once again, to know for sure if this is a straight line or a curved relationship, though, we will need the other 5 data points. 5 data points are good, but they're below our minimum. The absolute minimum should be 6. And since we're not at 6, we should collect more. All right, this will take us to our final data table and our final set of data. This time we're looking at the angle in degrees of release. So at what angle are we releasing the pendulum? And the period of that pendulum. So the time it takes to go back and forth with the pendulum. All right, so angles, we're going to go from 30 to 75. So that's actually not the full range available, but it sticks within our 10 and gives us nice increments. You'll also notice too that I picked a larger range. Instead of doing by here where I went by twos, or mass where I went by twos, here I'm going to go by fives so I can cover a larger range of numbers. So let's get that in data. So I'm going to set my there. And I think I'm going to start small and build up. So let me get them to 30. All right, start the. All right, 20408. All right, and there we go, our first data point. Let's check our next one. All right, so this time we're going to release it now from 35 degrees. All right, there we go. Okay, 2.0537. All right, so there was an increase, but not a really big one. It's not as big as, say, here, where there's a good 0.2 increase almost every time. Here, there's a much smaller increase. So we'll talk about what that might mean a little later. Right now, though, let's keep it to all right. All right, 2.05. Oops, did I mess that up? 2.0536. Oh, I think I did. Let me redo that one. Okay, so 40 degrees. That's what I was doing. 40 degrees was what I needed. $20687. All right, there we go. So if you think about this, without rounding, I've gone from 2.0. With rounding, I've gone from 2.0 to 2.1 to 2.1 again. So it seems pretty flat, but there is a change there. So, and this is not experimental error. So there is something going on there, but it's not quite the effect we're going to see. Now, this is something we'll talk about in the next lesson for this, but for right now, I want you to keep this in mind. But let's check the next thing. So now 45-degree angles. All right, photogate on, back and forth, and 2.086. No shock there. All right, so let's keep going there. But right now, it definitely looks like it's a flat line. So we're getting really to the point where it looks like our data is coming out flat here. So this may also be a no relationship. All right, let's do our final one. So 50. All right, 49, 50. All right. Pendulum, so photogate timer and 2.1057. All right, and there we are. So take a look. We're getting a pretty straight, flat across line. We are getting changes, but they're not by much. Think about it. 2.0, if I round these all, so back here, I can show you what I mean. I'm going to change the format very briefly on this. Oh, you know what? I'll fix it later. But if I were to round this 2.1, 2.0, 2.1, 2.1, 2.1, 2.1. So if I were measuring less precisely as I was with the stopwatch, I would actually see that I'm getting a little change at the beginning, but very little change overall. All right, so that should get us through the collection of our 3 pieces of data. Now, I've shown you how to do the first half of those. You need to complete the rest yourself. This is, once again, your responsibilities to do that. When you are done with that and you can now fully see the shapes of your graphs, there is a follow-up to this, so you will need to make sure you followed and answered those follow-up assessments. It is a multiple choice follow-up assessment, and you can take it as many times as you want. I will post your best scores. So, other than that, was the end of part 2 of our integrated chemistry and physics B 3-part pendulum lab curriculum. Hopefully, you were able to get all the information we need out of this and get the information you'll need to complete this lab. If you can, make it to next week's session, which I will be announcing the specific dates, times for on Monday. And next week's session, we will be covering part 3, where we will interpret and manipulate the data on your graphs to derive a final equation. So we're not just trying to answer our hypothesis. At the end of this, we need to have developed an equation to describe how all pendulums work. All right. All right. So once again, thank you for tuning in. And I will see you then, or see you virtually.